So we're going to be very brief. As I said, we're very last, and as you can see, the screen is already turning green and yellow. So I promise we're going to be brief. But let me start, first of all, by congratulating and thanking all the cluster's participants. Of course, we couldn't have done it without them. It's been great fun. Also would like to thank the Smartgeometry, the organizers and everything. It's really been a great event. Some of you might know that actually I'm Bartlett faculty, so it's been really fantastic to mess around with many new friends in your own backyard. Nevertheless, today and this week I've been here as the head of the Institute for Experimental Architecture at the University of Innsbruck in Austria. I've brought with me three of the most teamwork capable, hardworking, and relentless collaborators. We're about 65, but I brought three, and of course I mean by that the three robots, and also as well, Kadri, Allison, and Georg. And so it's been quite fun. We have a quite good system that they are going to explain, which is easily transportable. So we brought it here, and we've invited people to apply for the clusters, and that's what happened. Just to contextualize slightly the project of robotic forming, it's part of a larger neomaterialist research project that I would like to call proto-robotic forming, proto-robotic. Why? I don't think that at this stage in time we can talk about a fully robotic, automated possibility construction system in architecture. So a lot of research has to be done on the robotic side, which means on the technology, on the hardware of the whole system, as much, of course, as of the software as we've seen today. That's why I call it a neomaterialist project, in that sense that matter matters, and technology and tools and machines matter at the same time. There are two main objectives to this. The first, as I said, is how we can use robots and robotic system as a way to bridge the scale and to extrapolate the fabrication that is quite easily accessible in a smaller scale through, of course, three-dimensional rapid prototyping machines, and how we can use robots to enlarge the scale. Of course, with the volumetric exponential increase in scale, there must be also a change in technology, in hardware, and in software. And one of the questions of this research is whether robots can allow us to do that. Of course, considering the huge material, machinic, technological, and financial repercussions that this volumetric increase in scale implies. The second is actually also quite banal research objective, which is basically whether we are capable of providing an alternative to the passive house requirements of insulation. We've heard before that cooling is more expensive than heating in some building in some sort. Innsbruck is one of the cradle of these passive house guidelines. Of course, being in an alpine environment, the heating is of course as important as cooling, if not more. And what happens, one of those guidelines is to basically pack a lot of insulation into cavity walls. So one of the objectives is the question, what happens if we extrovert the insulation material and we provide architects and designers with a huge new canvas for manipulation? So these are earlier research which is done here at the Bartlett, where we use foam as this new extroverted insulation material that can be used to articulate highly complex geometric, textural, and ornamental surfaces. A second part of the research, which is what we're doing here with robotic forming, is to investigate and inquire whether foam in its soft condition, when it comes in tubes, has a structural potentiality to be expanded and to be stretched into larger structural possibilities. It's obviously very easily transportable, it's very stiff yet very light, and it seems, as my colleagues will show, that it contains a kind of a DNA that seems to be quite equivalent to some of the growth processes that we see in nature. And with this, I would like to hand over to my colleagues to explain the various projects.
So when working with foam, with this very uncertain material, we actually discovered that It has several material self-organizational properties that for us as architects were especially interesting and is inspiring. So there on the left side you see our foam prototype, and on the right side you see an analogy from the nature. Here a bone section, a sequoia trunk, mangrove roots, bat wing tissue, cervical vertebra, and even it has some similarities with minimal surfaces, how they are formed. So to explain our experimental fabrication process, I will start with the material side of it. We used very standard polyurethane foam mixed with custom additives, plaster, hardener, water, and pigments. So we mixed it by hand manually until it got these viscous properties and started to build the filaments. And this was the point where we transferred the material to the robots.
Okay, a short overview over the robots that we are using. We are using industrial robots, the brand's bestseller so-called. They have high speed of 8 meters per second they can reach. Of course, we don't use that. They have a payload of 20 kilograms, which is for small products till up to one-to-one prototyping. They are highly flexible. We arranged to make a system that we were able to ship to the partlet here and to the Smartgeometry Conference. And they are affordable, so we bought 3 of them. The system is also an open source system. We call it like this. It should be good for research, and it should be also for training our researchers, our students. And we would like to bring these robots out of our lab, which will also in the future our main goal. It's also an important task that people or students, participants are able to make their tools customized. So all the tools that we used here at Smart Geometry had been done customized by students from Innsbruck or for the participants here at Smart Geometry, which is an important parameter of the process we would like to develop. The robots we are having are 3 ABB robots, and these 3 ABB robots you see on the left side here, how they were arranged here. They have a range of 1.65 meters, which gives us a lot of flexibility in space how to produce. The software, okay, wow. The software we're using is Rhino combined with Grasshopper, and the whole plugin from Thibaut Schwarz, which allows us to give quick access to the whole overall robotic system. So students or participants are able from the first or the second day on to work with our machines. Does it work? Allison, does it work? No. Okay, we go on. No,
So in order to allow the students to begin to get an understanding of this material, as many of them had never worked with it before, we decided to begin with manual tests. And so what you'll see in some of these first slides are some of the examples of what our students were able to do by hand. Now what you'll see is that we had if we go back, some very elegant results. But the problem is, really, because this material is so uncertain, there was no way to properly replicate them. So what a few of you have probably wondered is, why robotics and foam? And this is the reason. As you'll see in this video, if it plays, is that despite all of this handmade work, we've talked about the difference between hard materials and soft materials. With any material, there's some room for error, whether with wood or metal. There's room for human error. There's room for differentiation in the process. And you can still achieve very similar results, whether you saw a little too quickly, a little too slow, press a little too hard with the drill. But when you're working with a material that has such strict requirements in order to begin replicating and getting predictable results, with robotics you're able to introduce that level of timing, that level of control, that level of actuation. So as you'll see here, one test, which was arguably a failure. It's not self-supporting. We were not able to remove it from the robots. While it has some interesting spatial qualities, it's not something that you could see as a sustainable object, something that you could use and reflect on in the future. In the next test, we'll see that with a very similar process, but just very small, matter of less than a second adjustments in the timing, you get a completely different result. And that's something that the human hand would never be able to understand. So with this very quick way of being able to code, where we use an interface with Grasshopper, we're able to use the robots not simply as a tool, but as an extension of our own ability to make and our own ability to understand materials. And so you'll see here we have a test that we were able to remove and then could exist as an independent object in our exhibits. And so here you'll see another selection of the variety of results that you can achieve with the same process with very small changes in the robotic code, so very small changes in the way the material was actuated. And here you see what can happen with just very small differences in the mixture of materials. So the minute that you begin mixing the material differently, it leads to an entirely different range of results. So it's a very rich material, but also material that requires an unbelievable amount of control in the process in order to achieve a desired result. I was clearly not in charge of choosing the photography.
So during the workshop, our collaborators developed different strategies for fabrication. Here you see from Andre development with 4 control points. Khaled was investigating genetic algorithms to find the maximum range, maximum position with our setting to get the biggest piece possible. Then Jota, Özgün, Marilena and Denis were investigating very interesting spatial twisting kind of strategies. And we had a group of Andreas, Chris, Matthew, Dirk, Vladimir and James who really pushed the material properties and created objects that were bigger than we ever imagined possible with this material. And with this 3 control point setting, we also produced these objects that you could, one of them you could see there, you can see copies of the same process at the exhibition in White's House. So here are just a couple of images of pieces that were produced during the workshop. And finally, I just want to thank all the collaborators and I think especially our amazing Richard Agneta, who helped to manage everything. And we are very much looking forward to next points in this research. Thank you. And if anybody didn't get the chance to see the exhibition, we brought some of it here.
So can we quickly have all the clusters back up, including the collaborators? And Sarah Jane, if you'd like to come back up to the stage. Well, we might start taking the first question. Manny.
All right, questions from the audience? Looking for hands. Oh, up here. Oh, go ahead.
Hi, I'm just got one question about the foaming technique. Did you do any systematic testing? Because it's down here. Because you show this small difference and you get failure. Did you do any testing of why and how and systematically?
You guys like to respond?
No. We tried our best to replicate over and over again the recipe, and in the end, we really found that the timing of getting it onto the robot and the sort of textures that we were able to develop just before actually extracting the shapes using the robotic arms was really the essential characteristic to getting a good stretch.
Yeah, so my question was about basically the same, so I'm just going to ask another one. So timing is of the essence with foam as is mixture, if I understand. Did you also try to simulate that behavior in some way, or did you just came up with like a lucky mixture and kept on using that one? Because I know, for example, you added resin to the foam. I'm just curious where that came from and how you dealt with that.
Yeah, so the mixture was something that they had already been working on before we started in on the cluster, and I think we just scaled it up and honed it. There was a lot of anomalies that came as we kept introducing other colors and other sort of variations on the mix, but in essence it was foam, plaster, a very important teaspoon of water, and then the color variations that we added and a hardener, excuse me. But frankly, the way in which we sort of were able to gain an understanding of the proper alignment and the proper timing to start extracting, and really to develop just by kind of pressing and pulling an orientation to the fibers just before starting to extract the form. Those two characteristics were the kind of primary phenomenon that we used or were looking for.
To share a little limelight with another group, but not to take anything away from the robotic foaming. For the volatile territories group, one question I have about both the RDS and then the processing-based work is it seemed to clump, and the question then is, do you have the ability to interject sort of geometric or spatial constraints? And secondly, do you have the ability to promote mixing? Because one would think that mixing is actually an important part of the programmatic adjacency question.
Okay, thank you. That was a great question. I think it's partly due to representation, that what you see in terms of the final processing solutions are a gradient of color, right? But in that color of, say, blue, for instance, there's actually a mix of programs. So that color doesn't actually represent the programmatic entities within that range of color. It actually it's the process of finding the adjacencies in that volume. So it's a bit misleading, seeing the color as a way to see that the process is working in terms of the gradients. But if you actually then, when we were exporting out the layers, and when you start to unpack the layers, so if you saw that one group, I think it was Nicholas, this group here, they had the actual range of colors was the programmatic range. So what you saw was a huge mixing of program, because that's what they had found in their 4D space, their design space. So in terms of the, again, I think one of the things I started to touch on was it's really about playing between intuition and complexity, and it's really about finding that environment in which we can design in. And what I don't think was quite clear, and we're not quite there yet, is a way to, we could fix those nodes while we were simulating, so you could get in and you could start to fix things. And that solution space, theoretically at this point, can be related to the bounding box of the geometry. So there is a relevance. So you can basically have an idea or conception of the sort of ranges you're working with. But ideally, I think what we're trying to do is actually move away from geometry to sort of unshackle ourselves for a minute and think about these other critical issues and find a different medium in which to design in that is laden with as much information as the sketch is right now, which will be hard to replace.
I have a question to volatile territories as well. I'm here. Hi. As I understand, the participants were provided with a processing code that you already developed as they started, and they were designing with this particular tool from day one. And in my experience, these existing tools make a lot of assumptions during development, and these can be a little bit restricting and also frustrating from a designerly perspective. So the first groups that you showed used the tool as they were, and the last group, the third group, could do some programming and tweak it a little bit for their own purposes. Yeah. So I was wondering how these two groups found, how they found their way around this existing tool, and how they could design with a tool, with a machine that came from someone else's mind.
Yeah. No, I think that's a great question. I'll pass it over to one of the group members in a second. But just first, I'd like to say that, again, it's about questioning the way in the realm in which we design. So there's a steep learning curve. I mean, when you start to work in a connectivity network, and obviously it's still on a two-dimensional screen, but you're essentially trying to inhabit that space and to recognize complex patterns that are emerging. And yeah, it's very difficult for us to sort of let go of our part T diagram, and it's not easy. It's only 4 days, and I think the group that did try to get into processing and try to adjust the code, I really commend them for doing that, and for David for really working with them. And I'd like to, I'm not sure if, where are they? Oh, right here. I think they could probably say a few words in response and what they got out of it.
Well, I'll say that, I mean, you're right. Like, we were given the software, and one of the first things I wanted to do was immediately dig into the processing code and sort of try and generate my own thoughts, let's say. And that's why I was incredibly thankful that, like, Dave provided us the code so we could do that. And then he was, incredibly helpful in, like, walking us through the code. And in that way, I kind of think that, code is so opaque that, or the program can be very opaque until you dig into the code. And so I was able to understand what he was trying to do and better able to use the software. So it helped us, not only we're not just changing the program, but understanding how I think Bruce and Elizabeth and Dave want us to use the program as well.
Can I add something?
Yeah.
It just, as a third group who was trying to tweak program a little bit, it was the difficulties we found. That's why we started to change it a little bit, because the program has been developed for the building, and we tried to upscale it into the urban processes, and we were missing those instruments of, let's say, time phasing and, let's say, dynamic. That's why we tried to let's say, emergence mechanism on urban scale, like social issues, when you actually can connect to the subjective data from internet and reflect it in quite top-down, well-arranged strategy which we develop into the software. So.
This question is to Sarah Jane. I'm just curious as to know how these ideas that you have seen here could inspire your work or impregnate it in some way.
So how can I take what I've learned in the last 12 hours into my work? Is that the question?
Yes.
Well, there are lots of programs and lots of designs and lots of systems that I obviously went, that's a fantastic way of mapping movement. That's a fantastic way of translating different types of awareness about moving through spaces. It's a fantastic way, if I have a ridiculously futuristic or speculative fiction idea, for instance, to build and construct using water itself as the architecture, I'm sure there are people here in this room who could help me visualize that kind of crazy idea. And likewise, if there are people interested in working in extreme environments, whether that's deep sea or in zero gravity or in altered gravity conditions or in desert locations and that kind of thing. I think it's really interesting to apply some of this thinking. That a lot of what I saw today was about the urban environment, but I think it would be really interesting to translate that into more kind of extreme domains where the architectures themselves are either not present or they are based in nature, and therefore our relationship is significantly different with that. So yes, I've learnt a lot. I'm very inspired. So thank you so much.
Thank you. I'd just like to thank Sarah Jane and all our 3 final clusters very much. Incredible display of work there. We have to unfortunately bring this session to a close now. We're going to get kicked out of the building in about 10 minutes, and there's a few closing remarks to come between now and then. Thank you very much.